Some people reflected, and I noticed myself too, that the week 9, no sorry, the week 6 video, somewhere around the middle, the projector screen or the blackboard or the screen share part of the video had some dropout for a few minutes, and then it came back on again. And it seems like it was a bug in the video itself, not about the NTU Cool or the upload. So I'm still checking. I mean, I noticed it, and but I haven't had time to look at it, and I'll take a look to see if I can restore it or not. I'm not too optimistic about being able to restore it, but it is what it is. So that's what if it didn't record, or if it recorded with some bug, for maybe some circuitry went down or something. There's nothing much we can do at this point. But the good news is that, I mean, it was coding anyway, so the code was there, and it was just a few minutes. So I think for the most part, it should be okay. All right, but so just take note of that. The video dropped out for a while, and I'll see what I can do about it, but apologies if there really isn't. Okay, so for today, we're gonna carry on with backpropagation, and we're gonna use a code that instantiates a multi-layer perceptron to demo the backpropagation code, how you would code it. One big disclaimer for today is that a bit of history. I coded this originally in R, and then over the years, I decided to move to Python because, and then from translating from R to Python, it worked for a while, for a few classes, and then just recently I discovered that it didn't work anymore, and it's not my fault, it's Python's fault, because they changed, they upgraded versions and all that, and some of the way I coded previously, if I reran it, and it was like it doesn't work. It complained and all that because versions, the functions changed. So then I tried to fix it and all that, but at this point it's not fixed yet. Okay, I just didn't have time to go through all the details and all that. So that's a pain with coding. Sometimes it's like the language or the administration, the core administration, they change things, which is fine for overall efficiency, but then if you don't keep up with your package and if you don't freeze your versions and stuff, you run into these errors. So lesson learned. But in any case, the core architecture, the core code structure and all that is the same, so we'll still go through that today, okay? But just the current code as you have on the NTU Cool, the Jupyter notebook link that I shared, if you run it, it will not report any errors, but the result won't be a learning network. Okay, it's churning out some numbers, but it's not learning. And I know where the bug is, but it takes time to kind of fix it. Okay, because I need to know like I need to know the version, what it requires. Okay, but so today what we will do though is still go through the coding thing, and it doesn't matter because next week is still backprop anyway. So it should be fixed by next week, and I can show you the evaluation parts, no problem. Okay, for today we will just go through the coding logic anyway, and I'll show you the code, and then that should be it. Okay, that's the most important part. But before we do that, last week we had all the backprop. I'm going to show you back on the screen. Excuse me. Last week, we had all the backprop theory. We went through the backprop theory, and I'd just like to pull up again one part so that I can highlight one additional part I want to cover for the first part of the course today, the lecture today, okay? And then after that, we will go to the online thing. Okay, so, I wonder if I can. Yes, I can. Okay, so this is just the Blackboard notes theory from last week. And the real key thing is right at the end here. through that. Right. Oh, I guess it's kind of a mess. But I'll use this one. It's easier. Not as messy. Okay, this representation. Can you see? Okay. All right, so this first part here. Okay, so in backprop, right, the algorithm will require us to do a feed-forward phase for the initial input. Okay, so I give an input, and then I use the weights to modulate the input to give rise to the activity of a subsequent deeper layer unit, right? Okay, and then you do this for all the units, and then you feed forward the activity from the input, okay? And then you learn a delta, right? There's a learning of the delta here for the output layer. And then this delta is used to update the previous layer weights, okay? And then also this is and it is also incorporated into the delta of the previous layer units, right? And then this previous layer units, the hidden units delta, is then backpropagated back to modulate the previous layer weights, and then calculate the previous unit delta, and so on and so forth, right? And then you feed forward again with some new pattern, and then you calculate the delta, and then you backprop again, and you keep doing this. Okay, this is how the weights updating in backprop goes, as we covered last week. Now, one part I did mention is that if you keep doing this, okay, just with the input, propagate the wave, feed forward wave, calculate the delta to have the propagation wave, to update the weights are going to go crazy, go out of control, okay? Because what you will do is you will, let's say you have 10 different patterns to learn, 10 different mapping. Remember, we want to map any input to any output. Let's say we have 10 different input-output mappings, okay? If you do this just as it is, okay, you will be adding the delta weights, the change in weights of the 10 different input-output mappings, right? Okay, you will be doing it like as if there is no normal range. You would just be adding. Remember in Hopfield network, when we do the weights, A times 2A minus 1, 2A minus 1 is the weights updating. And then you just sum it, right, across the different patterns, right? And remember, the more we ran it, the more crazy the weights got. Like at first it's minus, plus, minus 4. Then if you train it again, it becomes plus minus 8, then plus minus 16, exponentially, etc., right? Okay. Similar thing is going to happen here in that if, as it is right now, we are going to add the change in weights over iterations. And if we don't adjust anything, it can theoretically go to negative delta W to, infinity W, okay? So the weights will go crazy as it is. So what we do to account for this is to add what we call bias units, okay? And I'll go through that this morning. So right now, as I taught you in the previous lecture, we didn't talk anything about the bias units. And so today I will introduce that to you because you're going to need that to understand the code a little bit. Excuse me. Yeah, okay? So then now let's get to where the bias units come in. And to do that, I'm just going to hash the network again. Make sure it's white. Okay, so I'm going to just do 4 units, and then maybe 3 deeper units, and then maybe 4 units out here, okay? Now, the cycle goes that I will be going, I'll take this particular unit for this layer. Okay, so in this case, we're going to say that this is a 4, 2, 4 kind of architecture. right? And I'm going to take that asterisk, the star unit for the hidden layer as focus for now. And then from this one, I will take this one, okay, this star unit, okay? And this is the classic representation we use. This is the, oh, sorry, this will be the J. Okay, and then this is used to backprop the error. But we are talking about when bias comes, remember the problem is in terms of the updating of the weights, the learning of the weights, okay? So first, but when we talk about adding a bias, let's see, feed forward. In terms of adding the bias, we are worried about, we do it at the feed forward phase first. Okay, so we're talking about the feed forward phase of the error learning algorithm. And the first part is in order to control these weights, okay, for not going out of hand towards infinity or negative infinity, okay, in order to address this problem, okay, we have to secure a baseline. So to prevent this by adding a baseline or an intercept, which is the baseline, right? And let me classify that this is the problem. This is the method to adding a bias. Okay, all right. So the reason why we add bias units is because we want to account for the fact that if we don't, the weights as they learn over time have the opportunity to go from negative infinity to positive infinity. There's nothing to restrict that in the algorithm for feed forward and backprop. So and we don't want that, that's bad, okay, because when things go to infinity, it kind of loses its meaning and dynamism, okay? And so we want to keep the weights within some reasonable range of the data. A reasonable range of the data is the mean of the data, right? Where the data are usually found on average in the environment in terms of the numbers and the levels of stimulation of activity, right? That's a good estimate in statistics that where are things roughly happening in any data set? Well, roughly happening plus minus around the mean range, right? So numbers wise, so the mean is the best estimate, assuming you know nothing else of the data, right? Okay, so and that's actually what the intercept is. If you go back to your general linear model, okay, this is the intercept, right? Okay. And it will basically, if we go to the, if we plot this out, this is what it looks like. Right? That's where the intercept is. And that's the mean, so to speak, or some sort of a baseline, all right, in a regression model. And it's just a simple scalar, all right? And what it does is it locks. So all the other data points, all these other data points, and perhaps even the negative ones, okay, if you were to project back, okay, are going to be ballpark around this central point or this baseline point. It doesn't matter if it is in central or below or whatever. You can always shift the intercept, okay, but it is a constant scalar, all right, with respect to the data. And all the data that you are going to estimate or kind of adjust or whatever will be locked in because your intercept is fixed there. So you need an intercept term in order to have this regression line behave well. If I don't have an intercept term, my line can be anywhere in infinity, plus minus infinity, right? In statistics, that's what it is, right? But because if I lock in and I assume first there is one constant, and everything varies around that constant, that makes my statistics a bit more comparable across other data sets, between one data set and the other data set. So this is the so-called the theory behind why you need some sort of a baseline, and why therefore, and this is what we actually call the bias, all right? Is that we have a possibility that the data can range in all infinity, but no, we want to bias it so that it will always range around some fixed point. And that's a bias, okay? Any questions about that concept first? All good? All right. So if you understand what how intercept is related in the general linear model is related to the notion of a bias. It is a bias. And if you understand the notion of what a bias does in basic regression, you will see that actually the bias, if I were to add a bias unit here, so I'm going to let's use blue for bias, okay? I'm just going to add another bias unit here, and it's going to have a weight let's call this weights bias to H, BH. Okay, because this is H1, right? Okay. I'm going to add a bias unit to, in fact, every layer that's not the output layer. I will add a bias to the input layer. I will also add a bias, another bias, okay. To H2, yeah, okay. Oh, sorry, in this case it's J already, so I don't need that. And in fact, let's call it, because I want to distinguish this, so I'll call this bias 1. Okay, there's a bias for the input and a bias for the hidden layer, and every hidden layer will have its own bias. Okay, so we will have these weights that will be calculated as part of the error backpropagation phase. Okay, to instantiate that, if you see this, you will see that this is actually not here, but this is x so-called equals to 1, okay, xr1, xr2, xr3, xr4. This is going to be beta 4, beta 3, beta 2, beta 1, beta 0, right? And if I write things like that, do you realize something? Actually, what your input vector matrix and the weights array, if you do the dot product to give you the subsequent activity, is exactly general linear model, isn't it? Right? It's exactly general linear model. Okay? And therefore, the bias unit is just this part. Okay? And it can be estimated. So therefore, this is estimated. These weights are estimated. All right? And they adjust the rest of these weights, because these weights are always relative to the intercept, isn't it? Its change in x given that beta naught is whatever value, right? So in other words, all these other values are going to be tied to this beta value, whatever this beta value is. And we set it such that this unit, this bias unit, is always going to be equals to 1. This bias unit is always equals to 1. These other units, they can vary. They can be 0, they can be 1, they can be whatever you want to put. But the bias unit will always be on. That way, the beta naught or the WBH1 will have a fixed contribution all the time, regardless of how the other input nodes in units are varying. And in that way, it instantiates an intercept. It's always on. Okay? It's a constant. It can't be 0 because 0 multiplied by the beta naught will result in 0 contribution. So what's a constant that is not 0, that's nice and convenient? Well, 1. Okay? You understand it? Okay, so this is, traditionally bias units are always very hard to understand for people because it's like, what? This is weird. It's like, I just put input there. Why is there suddenly I falsely apply a bias in there? It is part of what we call the normalization. We have, which is actually neurally plausible, normalization. Okay, this phenomena, this adjustment is part of what we call normalization of weights normalization, all right, to avoid inflation, explosion, or diminishing, okay, which is this problem that I just said. This is about explosion, okay, and the normalization keeps the weights within some range. What's a neurophysiological phenomenon that reflects this? Well, your brain doesn't infinitely make your neurons active, and then infinitely active, right? Your brain has some sort of a range of energy that it can use, after which it plateaus. It doesn't get more active, and it doesn't reduce its activity until it's like less than 0. It doesn't do that, okay? So there is already some sort of mechanism in your brain that keeps the activity of each neuron at some baseline level, and around that level it fluctuates, isn't it? Right? So that's that part coming in. There are other ways to do the normalization. This is just one sort of mathematical trick. Is there such a thing as a bias unit neuron? Like one neuron that's always on, that regulates everything? No, right? I would argue not. It is a hypothetical mechanism. Yet your brain has some sort of overarching system that's so-called always on, and then around that on state of whatever your brain is doing, the neurons or sets of neurons collectively being on together, okay, that then the other neurons that carry the variance information will fluctuate its weights around that so-called on baseline state. Okay, so it's not one single neuron. You might think of it as maybe a network of neurons that are so-called always in the on state, and around which the other neurons fluctuate. That is plausible, right? So that will be more reasonable, okay? And then it's up to you to think, well, does the brain have such a neural system that's always on, and then the others just fluctuating around it? There might be, right? Not in the always constantly on state, but at least relatively, there is some sort of a system like the default mode network, right? That is sort of always on, even if you're not thinking, or even when you're thinking about other things, it has to be always there. Other things would be like even your visual system, right? You're not really processing anything specific, but your visual system is always processing something in the background, and it is about the contrast that is important to the visual system, isn't it? Similarly, your auditory system. So it's like there's some sort of a base state you can imagine that your system is having, and the other variance information is being carried out in terms of contrast processing. Got it? So this is to kind of bring home and introduce you to the idea of bias, its importance, because without the bias, the code will not work. So apart from the engineering algorithm reason, okay, physiologically, it also seems it makes sense that your brain does sort of have some sort of a baseline state and then it fluctuates around there. Okay, and if you were to take that baseline state away, yeah, you probably would really do some great damage to your brain's psychological processes. Okay? All right. So now the way we would do this is that we would put, if you have an input, let's say your input vector is size of 4, okay? This is the input. Let me use another color. This is your input, and it has size 4. What we would do in the algorithm is for any input, and if we specify that it is a 4-to-4 network, for any input size and for any architecture units sizes, what we would do is we would artificially or purposefully, intentionally add one more bias unit to the size of the input and one more bias unit to the hidden layer. Okay? And we don't do anything to the output. The output is what we want, right? But how the network itself works needs a bias correction, and that's where we would add augment the size of the units of the input and the hidden layers. That's how we would do it. Okay? Then we would initiate the weights. Okay, so these weights. So let me draw this because it's getting messy. So 2, 3, 4, and then put a bias unit here like this. Okay, 1, 2, 3, bias. Okay, and we don't do anything to the output. Okay, so what we would do is we would initiate the weights, these weights, and we would treat the bias as having weights just like any other unit. Okay, and we will always set this to be equals to 1. It's always in the on state, and this can be 1 or 0, 1 or 0. Okay, and inside it won't be binary anymore because we're going to use the sigmoid shape. We're not going to use the activation function. It's going to be sigmoid shape. So that means these units won't be zeros or ones. They will be floats, okay? Decimals, okay? And so we would add these we will add these units, set them to 1, and then we would apply random weights, okay, in the initial state, all right? Initialize some random W's, okay, which includes the input bias units as if it's one of those units, all right? When we do the feed-forward propagation of activity. Now, the thing is that these will connect, so I'm going to use a different color here. These will connect like this. All right, so it's good that I only have 3 colors. So then I'll do this one, this one, this one, this one, this one. Okay? But the previous layer, the input layer, will not have any connections to the next layer bias units. There are no input connections, okay, to bias units, only outputs. Okay, so that's what we will do. We will implement bias units, set them to 1, calculate their weights, but set the weights that will link to the next layer's bias unit to 0. There are no weights there. Then we do that again. We'll have a bias unit for the next layer, and we'll calculate the weights. And if there are more hidden layers, we'll set those units, connections to potential bias units to 0, and keep doing that. And then, when we learn the delta, and we backpropagate this, okay? The delta J that is used to modulate, to compute delta H1, right? Okay, and also to compute the change in weights, we will update. This will have change in weights as well. Okay, the bias units, they do have weights, and those weights can be changed. And in this way, they keep the range locked to some level. This itself actually is the intercept. I mean, right? Not really the units are not the intercept. It's actually the weights that are the intercept. The unit is just the one that keeps the intercept alive. That's all, because it's always 1. Okay, so, because this is the x, and this is the beta 0. So it's the beta 0 we want. Okay, the x is just to to keep it on. That's all. All right. Got this? So let me repeat one more time, and then we'll go to the code. We will set up the bias units such that every input and hidden layer will have 1 additional bias units. Bias units are always on. They have feed-forward weights that will also be updated, just like any other feed-forward weights. When it comes to the backpropagation phase, they will also be updated along with all the other units' connection weights, but they do not receive input weights. Okay, and essentially that's how this will work. Then this is when we do training. So in train, we have the feed forward, then we have the backprop. Okay, this is train. In testing phase, we only have the feed forward, and we do not have bias. There is no bias unit to feed forward when we test it. Okay, so when we feed forward in the testing phase, what we would do is actually take out the bias weights. We would remove this. Okay, we would remove this one. This one will all be cancelled. And we only care about the feed forward for the original units. Okay, so we only use bias during training. And when we do testing, they don't exist, right? Because your brain has now been trained to process the contrast. So when you want to test it about the contrast, you don't have to have that locking, because you're not going to update the weights anymore. The weights are not going to go out of hand. They're just going to be active, right? So you only care about the contrast-related activity. So you don't care about the bias anymore. Okay? So this is the overall picture of where bias comes in. You can understand why this is a separate topic on its own. This is itself also quite involved. Any questions about that? Yeah. Yes, 1 bias per unit layer. Yeah, so when you do the weights, remember, in general, what did I do? Yeah, alpha. No, sorry, it's not alpha. It was eta, right? Eta, delta, and activity plus alpha. Previous weights, right? Right? That's the general form. I'm not doing the indices, but this is the general form. Okay, so this includes the bias. Okay, all this includes the weights of Aij plus the weights of the bias thing. This one will also be that. Okay. So the size of this, if you're asking, that's what you're asking, is that it will include the, I mean, let's just do it this way, right? Plus Bj, right? Like this. Yeah, that makes better sense actually. Does that make sense? So when you're saying that, like, do we include the weights in the summing up? You do that for the activity of a given unit is equals to the function of the bias for any feed forwarding to the subsequent unit is included, and the updating is included as well in terms of its weights are also updated for its weights to the output, but the bias itself does not receive any input. That's the only thing, is that it does not receive this one. And I guess I might as well use this thicker line. Yeah. This green connection weights do not exist. And so there's no green connect. If it existed, it would be updated, right? It would have W's and it would have change in W's, right? So there is no such thing as there is no such thing. Right? There are no IBs. There are no HBs. There are only BHs and BJs, but there are no IBs and IHs. So there, in terms of the feed forward and weights updating, that's how that would play out. And if you want to sum them, yeah, IJs, BJs, and IHs, BHs, they would sum up to, but there are no IBs or HBs to sum up or change. Does that answer? Okay. Any other questions? Okay, if not, then we will take a 10-minute break. This is a good place to stop, and then after that we will come back and then we will go through the code, which I can tell you is a nightmare. All right. If you thought hot field was complicated, I mean, backprop is really a nightmare. Okay. The general recommendation is, of course, there are very nice packages out there, PyTorch, TensorFlow, and all that. They do LLM now, so they do backprop like so easy. You know, you can just tell the AI to do it. You don't even have to code, right? Just create like do backprop for me, right? Yeah, but you don't understand how it works. Okay, so now we are going to avoid all of that and try to understand how it works. And it is a nightmare to code in the sense of it really tests your working memory, okay? And also in terms of your logic and all that, okay? But if you understand how it works, I tell you, your confidence about LLM and all that will be at another level, because it's like, you know what they are basically doing. It's nothing so-called magical, really, okay? It's almost like it's guaranteed. Of course they would produce that kind of thing if you understand how the code works. Yeah, and that's the point. That's what we want to convey here. It's like it's nothing really black boxy about what they say about AI. It's not. It's a very complex machine learning tool. And they are, in a sense, somewhat predictable in a chaotic sense. Chaotic doesn't mean that you can't sort of, no chance of predicting. It just means that it's difficult to predict, that's all. Okay? All right, so let's take a 10-minute break, and then we'll come back and we'll dive into the code. Okay, shall we go to the code? Okay, so like I said, because of previously I was in this course I was teaching in R, and I started the course basically coding in R, and then in the middle I converted to Python, and it worked for a while, and recently I just realized that Python changed, and some of the previous functions and usages are no longer have gone have become no longer no longer relevant. So there's this code that I have right now. It will run without error, but its performance is not going to learn as it should be learning. Okay, but I know where the bug is, but it just takes me time to fix it. So I do think that it will be fixed next week, but it doesn't matter because the structure is still going to be the same. Okay, so the principle is we are going to implement what we said just now: feed forward, add bias units, feed forward, and then calculate delta, backprop, and then do this for the number of patterns that we need to learn. Okay, so first, just to refresh, in any coding for neural network, just like in the hot field, we're going to skip all this first, and then I'm going to go all the way down. It is critical to first define your problem, your goal, what you want to do. And as we stated last week, as it's different from the hot field, which is about doing memory, okay? Here, what we want to do is to do mapping of input to output. And we sort of did this at the single layer perceptron before the logic gates, AND gate, right? 0, 1, 1, 0, 0, 0, 1, 1, and then map it to either output to be supposed to be 1, 0, 0, 1, whatever. And we found that the single layer perceptron can only do linear problems, okay? So now, so there's a constraint there. It can only map linear problems, which is not very helpful, okay? You can do that with mathematics, and in fact, that's how a calculator works, okay? It's linear, okay? The neural network is different from a calculator in that it can do non-linear mappings. In other words, it can map anything to anything, and that's what we want to try to do. And in other words, we have to, as suggested, we can't do it just with one single layer. We need to do multi-layers. So we need to implement input states here. So this is the activity input array that we want, the input pattern that we want to teach this neural network, this multi-layer neural network. And we want it to output some desired categorization, let's say, or judgment or decision. So for example, bring it home to a real point. Let's say if I give you, excuse me, if I give you this set of features, and let's say this is about having fur, and this is about having 4 legs, okay? Like this column is about having 4 legs, and this column is about having fur, okay? And then the rest are like that you have leaves, are you green, whatever, right? So then these 2 vectors might be what we call animals, okay? Both of them are the same, they are animals, okay? But then the rest are like, yeah, they have leaves or green or whatever. Then they might be trees. Okay, then the next 2 might be fruits, okay, for whatever reason. And then the last 2 might be, well, I don't know, vehicles or man-made stuff, okay? All right, so in other words, I want to give this network some complex, very nonlinear pictures or set of features. And I want it to recognize that these sets of features, if they are on, means this kind of category. These other sets of features, if they are on, means other kind of categories. And maybe some of them they're not orthogonal. Some of them are like, sometimes they have both category features. Like they have 4 legs, but they're green or something like that, all right? Then you can do this. You can do this mapping. This is nonlinear mapping, all right? So mapping any input, for example, as we see in A, to any output as we see in O. And we have to use a multi-layer perceptron. And in this case, I'm going to, you will see in the code later, I can have the capacity where I will give it A, I will give it O, and I will define that it will be a 10-3-4 network. So if I go back to the notes, you will see that, for example, this is a 4-2-4 network. Okay, here on the board here is 4-2-4 network, and we want to have a capacity for our neural network to be able to do things like, so if we have a 10, if we have a 10, 4, 2, then it's like 1, 2, 3, 4, 5, 6, 10. Okay, 1, 2, 3, 4, and then 1, 2. So it will look like this. We might have a 4, 8, 4. So it will be 1, 2, 3, 4, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4. Okay, so it looks like this. This one looks like this. Okay, and then we might have like interesting ones like 2, 3, 10. And that looks like this. Okay, so, or you might have 10, 4, 4, 5, 2. So to be like this, right? Right? Pretty cool. And then like you might want to have, I don't know. Yeah, this one is pretty common now. Yeah. Something like that. All right. These are like pretty cool standard network shapes that you will see in the last few lectures. We will come back to it because one of those is what they call generative adversarial model, and then you have a recurrent models, and then you have well, deep. They are all deep models. But then these common names that you hear of, okay, you'll see that this is where you can go crazy. So you have to give your network, and you feel very cool about it because you can code your network to exactly do that, okay? And so you want to give our network the capacity to have this kind of, we can define the way the layers are set up, the shape of the network, the architecture. Okay, so in other words, we can implement a multi-layer perceptron, okay, that will take in any input and any output and map it. So that is the problem. That is the challenge. So how are we going to do that? Well, we're going to train our network, right? And we're going to train the network this way. Let's see. Yeah. In my code, the libraries are pretty standard. We set this up, okay? And the first thing I code here is how to train the network, which is how to set up the network architecture and then have it learn the weights given the input-output mappings. So the first thing we do is that recognize that this function, we're going to set it up as a function, a definition, because then we can use it easily in our simulations later on, okay? So it's a nice packaging of all this training algorithms, steps into a function called trainNet perceptron, so that later on, all we have to do is call trainNet perceptron. Give it the input, output, specify whatever architecture, and its output will be a trained set of weights. So just like the hop field, you have a trained hop field, right? You put in input, you want it to remember and code this, and it outputs a W, which is now the network that has some memory, right? And you can use it to be tested. Similarly here, we train some initial W, which can be nothing, which can be untrained, or pre-trained one, and then we want to train some more. We give it an input, which is what you want it to take in, and a desired output, which is what you hope it wants to produce. And then you specify the units layer here is what I have is called the architecture. It's the 10.4.8.8.4.8, whatever it is, or 10.4.4.4.4.5. And epochs, error, eta, and mu, these are hyperparameters. What they are is to control, as we had before in the hop field, how long, how fast do you want the network to how much time do you want the network to think? How fast do you want it to learn? Because, for example, eta is the learning rate, and mu is the momentum. We talked about this last week, right? if the learning rate is very big, then it will consume the error more. If the momentum is higher, then it will be a bit more like, slower, right? It will want to be sluggish. So these balance out how fast you want the network to learn from new information, or do you want it to keep the old stuff a bit more? An error would be kind of like some thresholds. You always need a threshold, right? Of how much tolerance you have before you think the network is, stable, something like that. Okay? Okay. So these are the minimum pieces of information that you need this function to have, to input, to give to the function. And based on that, you set up initialize some parameters. So for me, it is about putting in setting up the shape of the inputs that I'm going to have. So the function needs to know, well, how many inputs do you have, right? So for example, just now I had inputs that might be 4, size of 4, or inputs that I might have 8 units or 16 units, okay? Like for the hot field, we have 16 units. So this would be the number of input nodes, basically. And then number of patterns, NPATs here, okay, is because if we go back just now, if you saw my A and my O, right, I had basically 8 input patterns and 8 output patterns, right? I had 2 for each category and I had 4 categories. So I have 8 input-output patterns. So I need this multi-layer perceptron to learn to decode 8 different patterns. All right? And to know that in these 8 different mappings, there are actually 4 classes, right? 4 different outputs that I want it to encode, that I want it to learn. So the number of patterns basically tells this function that there are 8 patterns to learn, at least within this simulation, okay? And then extract some information about the number of layers. So in this case, if we do a 848, then it's 2 layers. Number of layers is not about the units, it's about the weights, okay? So the layers are, if you have 848, then actually you only have 2 layers, okay? If you have 3 layers, it will be 8485. Then there will be 3 layers, for example, okay? And I get this from the units layer and then size -1, because my units layer has 3 numbers, right? 848 is 3 numbers, but I only want it to have 2 layers because it is 8 to 4 and then 4 to 8. So I have 2 arrays, in fact, right? So yeah, I can draw on this one directly, right? So units layer, if I do 8 for, let's do 3, okay? What that means is that my W here is a 8 by 4, and that my W here is a 4 by 3, which is 2 layers. So this is units layer. Later on, when I input the function, it's going to be a vector of 3 numbers, 8, 4, and 3, which specifies that there is 8 inputs, 4 hidden, and 3 outputs in the way I define it here, which means that there will be 2 layers of weights. The first layer having 8 by 4 connections, the second layer having 4 by 3 connections, all right? So that if I wanted to calculate the number of layers, I simply get the size of units layer, in this case is 3, and then I minus 1, and then it's 2 layers, right? Okay, so that's the logic there. Okay, then I initiate some temporary weights, WT, and holding of the temporary weight. That's why it's gonna really work your working memory here, okay? Not only do you need temporary weights, you need to hold them, and then you need to know when to use them, when not to update them, and all that, okay? And the reason why will come in more obviously later, okay? It's not so simple like I just want one weights and I just update, because if you update it, you lose the previous information. So you have to hold some temporary holding pattern, update some patterns, and then like integrate the holding pattern when you want, and then hold some more and all that. So you need to be able to balance between what you are updating and what you're holding and being careful not to lose information, because it's very easy that as you update, then it's like, oh wait, no, you actually needed that. I shouldn't update it. Okay, so that's why I have initialized these temporary waits over epochs. Okay, waits over time. In fact, this will be the output. Okay, this will be like, let's say I want it to train for 1,000 times, then WT will be a tensor, in fact, okay, array of arrays that is of size 1,000. If I train it 1,000 times, it will have 1,000 instances of its arrays of weights. Okay, so and I'll have to have a duplicate holding of this equivalent train temporary weights. So I have a placeholder here. And arbitrarily, I'm just going to set, I want to have a starting point where whatever error I am satisfied with, I want it to be like start at whatever it is plus 10. And then I let it drop to like the error that I want. Okay? So this is how I sort of cap the performance. So this is similar to the Hopfield network, the number of or is it Hamming distance, instances that are 0, where then I declare that the network has stabilized. Okay, that's the equivalent here, is the number of times when the moment it reaches some threshold error, that's when I declare that the network has stabilized. Okay. All right. So initialize parameters done. Next thing is to add the bias units. So like I said, first things we do is we arbitrarily apply bias units because we need it to normalize. We need to lock it into some range. Otherwise, the weights have the capacity to inflate, explode. All right? So the bias units act as the intercept, which locks the estimates within some range. And you have to do it for each layer. Each layer will need its own bias unit, except the output units. Okay? So that's why for range in n layers, which is 2, let's say we're doing the 848, okay? Then your I will be a range of over 2 iterations. The first I will be 0. In Python, 0 is the first instance, and the next instance I will be 1. Okay? So for units layer 1, units layer 0, whatever that number is, just add 1 to it, right? That's where we say that let's say I have 8 input units. Well, now I have add 1 more bias unit, so it becomes 9. And my hidden layer, let's say, is 4 units. I add 1 more bias to it, then it becomes 5. And then my last output layer is, let's say, it's 3. Its output layer, I do not add anything. So the way it's written, it's not going to loop to the outer layer, right? It's only going to apply the addition of 1 more unit to the input and the hidden, but not the output. Okay, so that's what this, just to add 1 more number to the units layer architecture, that's all. Okay, I haven't actually changed the network yet. I've just sort of changed the input parameters only to update some information, and I'll be using this to actually instantiate the architecture as we see now. All right, so this is the part. So after we have updated in the initialized parameters, like we set up the holding arrays, okay, and then updated the bias unit information that we need. Now we use all of that to actually create our architecture. We are going to first assume that we have no initial pre-trained weights, right? That's the default case. In which case, we initialize with some empty arrays, or empty lists, okay? W and whole pattern W. Again, this is because we need to have the actual thing that we want to use and things we want to hold, which we don't want to, the actual thing we don't want to update yet. And we want to have to hold some information about what we are going to update later. And then later, when we are ready, we will update it. Okay? So that's why I always have these two W and holds. W something and hold something. You know, okay? You're going to see that, all right? Because of the way that we have to implement changing weights over different patterns and over different epochs. Okay? It's going to learn 8 different patterns, but it's going to learn these 8 different patterns over 1,000 times. So you don't want to, every time it learns, it update immediately, because then it's got a next pattern to learn, and it would have changed. And that makes things very complicated. In fact, it will not be able to learn effectively. You'll see. Okay, so we apply these empty lists to initialize the architecture that we want. And then now we qualify it, that we're going to have 2 layers. Again, we're operating with a 10.4.4 or 10.4.3 architecture that we hope to implement. So let's say we have 2 layers, and for the first layer, what we will do is we will have a holding or temporary weights that is consisting of random uniform numbers ranging from -1 to 1 of size k, unit layer first one, and unit layer subsequent one. So this is exactly, again, if I had 8, 4, and 3, right? Then this is 8, 4, and this is 4, 3, right? So this one is 8, this one is 4. So then I'm going to have a W, you know, -1, 0.5, -0.5, random numbers. That is going to be 8 by 4, right? Okay, so this is the first layer. Then I'm going to have another HHW. Okay, so this HW, okay? And I'm going to HHW is going to be all zeros, which is also 8 by 4. Just temporary holding thing, okay? Oh, sorry, it's not 8 by 4, I forgot. Remember, we added a bias unit, right? Yes? So actually it's 9 by 5. Okay? At this point, the bias units, the units layer have already been updated. Okay? So originally, although we wanted 843, in fact, we are instantiating 9 by 5. Got it? Any confusion here? I hope you get it, okay? Because we already sort of updated the units layer to incorporate that we need bias units. So the architecture we actually implement at this point in line 51 is going to incorporate the bias units already in its weights array. So although we want 8 by 4, effectively we implement a 9 by 5 in the first layer. Okay? All right. Then we remove the, because this is going to be, so the way it works is going to be 8 by 4 is going to be 1, 2, 3, 4, 5, 6, 7, 8. Then bias unit, okay? And then by 4 will be 1, 2, 3, 4. And then it's going to be a bias unit, right? Now, this has 8. And this, this has 9. And this has 5, right? Okay? So see, this is why it's such a nightmare. This includes this, right? So no problem there. It includes the bias unit having feed-forward connections. But it also includes this. That's why it's 9 by 5. It's complete, fully 9 by 5, has a row of bias connections, isn't it? But we said the bias unit does not take inputs. Correct? So we need to erase these. We need to take this one and erase them. Okay? We need to erase those inputs. So this is why we remove connection to next layer bias units by saying if this is not equals to if this is not output, because output does not have bias, so we don't want to run into an error. We only do it if it is not output, okay? For output, we don't need to do it. So this is just a catch contingency. So if we are now not in the output, so we are at the first layer, layer 0, okay? Then what we do is just set all columns, all rows of the last column last column of the W of the arrays, set it to 0. That's what these 56 and 57 do. Okay? Right. So the theory we talked of just now, this is the code implementation of it. Okay? Very like, you know, it's easier for you to get it now, but imagine you start from 0, nothing, scratch. How are you going to code it? Right? Yes, it's really a headache. Okay, yeah, it took me a while to figure this out. Okay, and this was just translating it from the Rumelhart and McLaren paper raw. Okay, no pre-guide. Okay, and back then no Google, no, and it's stupid R. Okay, so I know how much time I've wasted in my life. Okay, because now you can do this like. Okay, so this is what it all means, yeah, and back then no Git repo where you can download McLaren's code and then just run it. Right? So anyway, so you have this concept of instantiating the architecture, then adding the bias units with feed-forward connections, then removing the input to the subsequent layer, the input connections to the subsequent layer bias units, because that's how we do the normalization. In theory, why the normalization works, how we should do it, and so this is how we should do it in the code. Any question? This is not always very obvious, but I hope you see it. Okay, all right. Now, if that's all done, then that's it in terms of setting up, initializing the W and the holding matrices, the corresponding matrices. And then we just append it. Okay, because we only have one layer now. Now we add it, so this is going to be layer 1. Now we worry about layer 2. Okay, I'll use a different color. Okay. Why is it still the same color? Okay. Going to be layer 2, and layer 2 is going to have, do the same loop, but it's going to be 5, because it's 5 now. And because it's output, it's going to be a 5 by 3. Okay, output layer does not have bias units, but the hidden does. So the hidden has 5 by 3, and so it will implement a 5 by 3 HW and a 5 by 3 HHW, and because we are now at the output layer, K is now equals n layer. Okay, we are at the second layer now. So we don't need this. Oh, sorry. We don't need this part. I'm going to use red so that it's more obvious. We don't need this part. Okay, this part we want. We still want to append it, but we don't need to remove the input to the bias unit of the output unit units because the output units do not have bias units. All right, so the catch works because now that we are at n layer equals to 2, the code knows that, don't need to do this zeroize the last column kind of thing. And then just directly append this new array of W53, 5 because the hidden does have a bias unit that contributes to the total weights towards the final output units. Got it? So then, after you've looped through this 2 times now, for an 843 setup, you will have your initial architecture of this multi-layer perceptron at this point. Okay? Nothing's been trained yet. It's just initializing this with random numbers. Any questions? All good? All right. So now we are going to, I'm going to clear this one. This is very dangerous because I don't want to wipe out the other one. I'll just do this. Okay, so then if we're okay with this, I'm going to keep going. All right, so that is for the case of if I initialize from, initially like having no pre-trained weights, okay? But if I do have pre-trained weights, then this contingency, this part just does the same thing of adding the layers and bias and stuff like that, but just taking into account that I already have a W. So I just need to do the setup for the holding pattern. I don't need to work on W because W already has been set up. All right, so this is the second part of this conditional, if conditional. All right, and I also need to hold a 0 hold pattern, another holding temp thing here. Okay, so this is another just a placeholder, and it will come in handy later on. Upon second thoughts, sometimes if I were to work at it and make things more efficient, I probably don't need so many holding temporary things. But again, I was translating from my R days, and so I didn't have time to really clean up the code. So a lot of holding things being held all over the place, which may be actually redundant. We'll see. Okay, so we've set up our W, bias units and all, okay, with initialized random weights according to the architecture we want. All right. Now we go into training, that proper training. So first, the outermost wrapping loop is the epochs. So we want to train the network for 1,000 times, 10,000 times, 50 times only. This is the outer wrapping. Okay, so we loop for t in range of epochs. Okay. Another loop is it's a conditional loop, okay, or while or if total error at that moment is still greater than the threshold error. That is line 83, right? As long as the error of this network is still greater than the total error acceptance, then continue to learn. Then do the continue to train rather. Okay, yeah, okay, means the network is still not listening, so committing some error, so you have to beat it. Okay, 还没学好要打. Okay, sort of. So this is the error contingency, the error threshold implementation. Okay. Then we, again, set up some hyperparameter or indices that we have some measure. This is what pattern error, which is the error associated with this pattern. It will come into place later. We'll hold on to that. Okay. And we also set up a holding pattern for the momentum term. You'll see that come into play later on. Remember, the momentum is one of the hyperparameters we set, which is mu. In this case, it's very nice. It tells you that it is 0.7 as in this code. Elsewhere, we have already said that our mu is 0.7. So now Colab is very smart. Okay, it conveniently lets you know what you have set for this parameter here. And we multiply that into whole pattern, and we append it into the M, which is the momentum term. Okay? Now, whole pattern M has the same size as the arrays, right? Because remember, we want to update the arrays according to the function. The updating function is like this. I know I call it mu, but it is alpha in the equation. And for this reason, I do not like Rumelhart and McClellan and Roscola, Wagner, and whatever. Actually, it's not Roscola, it's Rumelhart. These computational neuroscience people just mess up all the standard convention namings. Momentum is mu, right? In physics, it's P and mu. Mu by P gives you momentum, position, and momentum. Okay, it's very clear, right? It's not alpha. Alpha is just some learning rate or something else. And then, but they use alpha in the theory. So just to help you make this mapping, I think more physically. I don't think so. Whatever it is that they're using is very weird. Okay. So in any case, the mu here is the alpha in the equations in the theory. Okay. Just have to make that transition. That's all. Okay, in any case, remember that we have to add the momentum term. So what I'm doing here is whatever learning we need from the delta later, but we need to account for that we also have to have some momentum holding it back. So I'm just setting this momentum as an empty placeholder here. And in fact, whole pattern right now is, if you look on top, the code is right now it's a set of zeros. So M at the right initial is just 0 for now. Okay, it will not be 0 later on. Okay. Okay. So this is just to set that up. Again, just something holding. And then after that, and this is where my bug is, because I previously needed an empty array or empty matrix to have another holding pattern and whatever not. And just the previous version of Python was okay with, and this has already been changed, but it's still not working. The previous version of Python was okay to set up empty numpy arrays with some other syntax. But then for some reason, after some version change, it didn't like it anymore, or it did something different. And then when I used the AI to try to say, okay, what do you use now? AI is wrong. Okay, this is what the AI told me to do. And I want an empty array, but empty like and empty does not actually give you an empty array, okay? At least not in the way I want. So I'm going to be fixing it. Once I fix it, the rest should snap into place. It should be okay, all right? So the only error here is that I do not have a holding empty array W as I want to hold things before I update. What that actually does, that line actually does, is it fills it with numbers. And the numbers are very crazy. And I have no idea. I mean, the idea is that numbers are uninitialized. They are not systematic. In other words, it's kind of like random numbers. And I'm like, well, why do you need something? I don't know. They say it makes better sense, and there's no point creating empty arrays. And I don't know. Sometimes people have their opinions. But so, in other words, this one, it doesn't work because it initializes an array that is not empty, actually. And because of that, it messes up my training later on. It doesn't mess up the algorithm. It messes up the numbers it generates. Okay? It will generate the numbers, but the numbers will be wrong. Okay? So that's one thing to note. But the point here is that I still need another holding empty array layer. And then for a given epoch, let's say number 1, for pattern number 1, remember, I have 8 patterns, yeah? A and O, I have 8 rows of each. Let's take the first row, A and O pairing, okay? A first row and O first row, these two pairings. For the first pattern, so for P in range of the number of patterns I have, first set the input activity to be empty and then fill it with the first input pattern P. Okay? This is just a comment for myself, just to check in case. But what this line does is to take the first input pattern, basically, okay, and put it into AI, A input, not artificial intelligence, okay, the AI or AJ or AH, okay, the AI. Then feed forward, propagate the activity forward across the two layers. So for the first layer, for K as 0, first layer, we set AI, the last unit, yes, to have it as 1, okay? Now, it is append because remember, the bias adjustment that we did just now only applied to the weights, the W. We only created arrays, weights arrays, adding the bias units. But we never actually increased the bias units, right, themselves. So this line will say AI, which right now has, let's say the first row of AI, I think had 10 units, okay? Now we want to make it 11 units, and the 11th unit having 1, value of 1. So what this line does, A of I, C input array setup below, okay, is size 1 by 10. Okay, A of I plus bias will now be size 1 by 11, such that A of I B 11 is equals to 1. The input bias unit is always on. It is always set to 1. Okay, this is a hard setting here, this line. And I do it for only, I need to only do it for the first one. For K is 0, the first layer, because you'll see that in the way I've coded it, subsequent layers will carry this forward. It will automatically then know that, oh, because you've already set the input, the original input to have 1 additional bias, then subsequently as you loop, it will set the other inputs to have a bias of 1 as well, okay? At least I think that's the way I have coded it. Okay, that's the idea anyway, right? So that I do not need to do this for every time. It automatically will if you see the code. Okay, all right. So set the input to 1, then now compute the activation for the subsequent hidden layer unit. So, oops. Okay. Right? Compute AH1, and what this does is AH1 is equals to 1 over 1 plus E sum of AI, like this, right? Which is the activation function, the sigmoid activation function. Oh, sorry, no, it is WAI. Okay, as WAI increase, at first is 0, then at some threshold, close to the threshold level, it starts to go up, and then after that it plateaus out, and it is going to be 0 and 1, asymptotic to 1. Never reaches 1, but asymptotic, and never reaches 0. It infinitely approaches 0 and infinitely approaches 1. That's what these two lines do. Now, you might ask, why don't I use NP exponent? Okay, why do I use this SciPy function? So yeah, it's a bit confusing here. So some of you who use Python will know that there is this capacity, the exponential function. Okay, numpy has np exponent. Why do I use the SciPy special exponent IT whatever complicated thing? Again, this is 很伤脑筋 like the 东西, okay? Because I used np x3 at first. And I realized that the numbers, the range that we play with, can go to so small, close to 0, that np exponent treats it as 0. And what happens if you have an exponent at 0 like this? This whole thing becomes undefined, right? Okay. So in other words, the reason here is that np exponent basically does not have the precision. The function, the code, np exponent does not have sufficient capacity of precision for this purpose here. Of this code, of the way we are implementing it. It might be okay for other settings, and there might be ways to get around it. For at least the way I'm using it, np exponent will result in undefined numbers. Okay, and it is because of the way it handles precision and arrays and all that. Well, because np is focusing on different things. It's focusing on array management. It's not focusing on computing precise numbers per se. Okay, but SciPy has this function for its exponent, and it can handle the precision that's needed. Okay, so that's the reason why I have to use this weird way of doing something that's actually very simple. And again, you have the fortune that I've already struggled with this long years ago, and then now I can tell you immediately that you should not use np exponent because of that. And no one told you that until you run it, and then you just struggle with it for a long time, it doesn't work, and then you have to go find out that, oh, it's because of that. And they don't tell you that, right, from the start. Right? They tell you that, yeah, of course you can do exponent, right, np exponent. Right? So, and then you have to do float 128. See, it's about the precision. Okay, float 128 means carry a float number up to 128 bits. Okay, imagine the precision of that. Because usually we are working with 16 to 32 to 64 bits is already really a lot, right? Okay, but the numbers we are dealing with here are in the order of 128 bits. Okay, but that says something about our neural network's precision. Okay, how precise our neural network is really compared to a machine. That it actually, our neural network arguably is more than 128 float bits. So, and we do it so effortlessly. Okay, so again, when you do this, you really learn amazing things about your own biological system. Okay, so this is the activation function, which is the part of the feed forward, right? So we have set up the array, we've added the bias units, and then we've set up all the holding things that we want. Now we start the first epoch, the first pattern, and we drive this pattern activity using the sigmoid function through the first layer and through the second layer. So this loop here, right? This loop. This does it for every layer. So the first layer to the input to the hidden units, and then the hidden units in the next loop, the hidden units to the output, so that at the end we get first AJ for the first pattern, for the first epoch. Okay? This is the result of going through, yes? AIK. Oh, here? Yes, here is, as I said, we need to add the, for the AI, the first input units, we have to add the bias. So this line adds the bias and sets it to 1. So let me, if you didn't catch that, let me reiterate this again. Remember, let's say I only want 4. So AI. Okay. So and if I loop it to the second time, then the AI becomes AH. It's just that I keep calling it AI. That's all. All right. So if K is 0, then it's AI here. Okay. If K is 1, then actually AI is AH as the loop goes. Okay? And so for every loop, it's going to add such that this is hidden bias unit is going to be 1. And I've only done it at K is 0 because, as I said, this will propagate later on to such that it will know to make the rest of the AIs also 1. Or at least I hope it does. I will validate it next week, sorry, okay? But that's what this line does, AIK append with 1. Does that make sense? Yeah. The 1 was added at the array already, but that was on the W, so that plus B, right? Remember? We added it at the array. The array has this connection. The array has this extra column now. Okay, this set of weights. The array has this bias unit set of weights. The array has. We did that just now. But the units, the nodes that are supposed to be active, we haven't added that yet, right? And that's where we are doing it now. Does that make sense? Yeah. So the previous ones where we did deal with the bias was bias weights, adding the weights to account for the later on that we are going to have bias units. Then now we add the bias units and set them as 1. So that then when we apply this dot product, the dimensionalities will match. Correct? Because at that point, this one, let's say it was 5 by 4 in terms of the size, right? 1, 2, 3, 4, 5. 1, 2, 3 plus 1, 4, right? This is size. But our size of AI without the bias was just 4. So if we do a dot product of this by AI, which is 1 by 4, and it is 5 by 4, right? That the dot product is not going to work, right? So we need to also do this so that this becomes 5, then it works. Make sense? Okay. Okay. With me so far? Having a headache yet? Okay, some point get really tired after this. Okay. Now, so we have now feed forward the activity, 1 loop. We're not even at the delta yet, okay? So now here we come the delta, the backprop part, which is really the magical part. So we compute an error, which is supposed to be at first, as I said, an empty layer of error units, but because empty doesn't work, that's why this doesn't work, okay? So I'll check this next week, but if it works like it's supposed to, it will give me an error vector that's first empty. Then I will fill it later, and I'll fill it with what? Well, I will fill it with this. Okay? Now, I will go backwards for range of the number of layers, but counting -1 backwards. Okay? That's what this means. So this loop will be K, at first will be now 2, or rather it will be 1, then it will be 0. At first, K goes from 0 to 1. Okay? Then now K goes from 1 to 0 backwards. That's what this line does. Okay? So I need to backprop. Then if it is the output layer, okay, so first start at the output layer. Now my K is 1. okay, which is the output layer. And so if k is equals to the n layer, and I will say it's minus 1 first because so I have 2 layers, so I will make k is equals to 2. And this, again, I need to check. And this is part of the transitioning from R to Python. Because R starts from 1, Python starts from 0, okay? But in any case, you start from the output layer. This is the output layer. Remember, our delta for output layer is different from our delta for our hidden layers, right? Okay, so if we are at the output layer, okay, which is what this is supposed to do, then the error of this output vector error is going to be equals to the desired pattern output that we want. D out is, if you didn't catch it, D out is the desired output, which is O. Okay? Outside of the function, the desired output that we wanted was A pattern array and O pattern array, right? Mapping of A to O. O is fed into this D out in this function. Okay? So D out is actually O. All right? Now, so the array, the error is going to be the desired output. Okay, so pattern O equivalently, the first pattern from array O, minus, at this point, AI, because K is the output unit, so AI K here is actually AJ, right, in our theory, the output activity. So desired activity minus the network's actual output activity. And you do the subtraction, that's delta, right? Multiplied by the activity of itself by the 1 minus activity by itself. What is this? This is delta AJ 1 minus AJ the derivative of the function, the activation function, which is the sigmoid. Remember? If you go back to your notes. Okay? So the error, based on the theory, for general functions, not just linear ones, is going to be the difference between the desired and the target and the actual output modulated by the derivative of the activation function, which is AJ times 1 minus AJ. Very simple. So that's what the error at the output layer is going to be. So this line is the critical line, so to speak, in backprop of error. Is here, line 1, 2, 3, is this line. Because from here, this error is going to be backpropagated into the inside of the network. Then we calculate pattern error. Okay? This is something we haven't talked about at this point, but it is a metric, kind of like energy in Hopfield, right? We just want to, or the Hamming distance, or the energy in Hopfield. We just want an index to kind of quantify like how far are we from the desired state. And in this case, you will see, what is this? Sum of the difference and square. So it's just basically variance, okay? Variance between the network's output and the desired output, okay? So that's what's pattern error. Then we calculate layer weight change, all right? So this is delta. Sorry, input. Where was it? Yeah. Okay. Plus, supposed to have a momentum term. We haven't added it yet, right? But now we just calculate the learning rate term first, which is from the delta, the error. Okay? You see where all these terms come from, right? We have already calculated this value, and we know this, and we know this is input, okay? K minus 1 is the input. So it's qualified by, the delta coming from the outside is qualified by this unit's own input that's caused the delta to begin with, right? So you put these two products, then you modulate it by its learning rate. That information is how much you should change the weight by, right? Think about it, yeah? So you caused me to make this error. So now I want to use this, how much you caused, how much error there is, so that now I want to adjust my weights to regulate this by some learning rate. Okay? Does this make sense? So this came from the theory, all right? And now there's supposed to be some momentum term, but we're not dealing with it here yet. Okay, we're just holding how much we need to change if we were to just only have the learning from error part, not yet the momentum part. Okay, so for now, for this pattern, for this epoch, we just want to hold it, this change in weights. Okay, so that's what this is. And then next, because we have bias units, okay, great. So we have to set the bias units to, no, the bias weights in this case, back to 0, but I'm thinking that I actually didn't need to do this, all right, because it's supposed to have no weights anyway, all right. So this line here, again, is something that I need to go and confirm to make sure that my code in the train station works. But other than that, you've already learned the error that you need to change for this given pattern, for this given epoch, for the output layer. Okay, so in the first loop, we only dealt with the output layer. Now we have the, if we have the 843 again, okay, this one. So now we have this one. Okay, now we have this one. We had the delta, and we brought it here, okay? But we also now need the delta H, so that we can also have the delta H that would update the hidden weights here. So that's what this next part is going to be. Calculate hidden error unit, and you can see it's a little different. Okay, so I'm going to erase that part so you can interfere. Take a look at line 138. Compare it with line 123 just now. I guess I will roll it up. Okay, compare line 138 with line 123. Can you see the difference? What are the differences? Well, first, line 123 is with respect to the output. Okay, and AI here is actually AJ. Okay, all right. Here, so that it gives you this. Okay, here now that we are in the hidden layer, we are actually getting the error from delta J. Okay, this is a relation from delta J. And then we also have the weights from the H to J. No, sorry, it'll be weights. Yeah, weights HJ, or JH rather, okay? And then this will be the activity of the hidden units, right? So in other words, for the hidden error, as we talked about in the theory, that the delta that is in the hidden units is a composite of the error that is backpropagated from the output layer and those weights that cause those errors and its own activity that caused those errors. So anything that basically made it wrong, that caused it to be wrong, is all multiplied together to give you the error that of this unit. Okay? Whatever caused this unit to be wrong is multiplied together towards this estimate of how wrong it is. That's what these terms are. Okay? And once you have that same thing, you have the eta. And then you have the delta term. And then you have the, now this is k minus 1, and this is now a input, the original input. So the change of the hidden weights, this one is similar in form to the, for the immediate calculation for the latest output layer. Okay, and then similarly, after you do this, I'm not sure if I needed to, but I do account for the bias weights as well. I suppose I might need to, otherwise I wouldn't have done it that way. Yeah, set it to 0 or something like that. Okay. Now, at this point, note, all I've done is hold this, put all these error learning thing, okay, for each pattern, right? So remember, I have 8 patterns, right? A and O, I have 8 rows. So what at this epoch, I have learned pattern 1, calculate the change in weights, but hold it. Pattern 2, I didn't sum anything, right? I just hold it. So I now calculate the change in weights for pattern 2 from still my initial random W, you know? So I haven't changed the actual W yet. That's why you see I need so many holding layers. I'm holding the W, but I'm calculating, I've got 8 patterns to learn. So I need to learn 8 different patterns of changes relative to the original W. So right now, I'm just having, 8 holding patterns, and now I want to sum it. So to be clear, I have 8 holding change patterns. I sum it so that I have a final holding pattern. I have to do it this way because imagine if I learn pattern 1, okay, pattern 1 is relative to the original random numbers. So I learn how much to change my weights relative to the original random weights. If I were to then, okay, so now update the weights. Now learn the change in weights for pattern 2, that's not fair. That's pattern 2's learning is now based on some modification from the first pattern that has been added into the random weights. So the random weights are no longer random, right? So if I learn pattern 2, it's not the same as when I was learning pattern 1. Subsequently, if I were to add this and then learn pattern 3, pattern 4, pattern 5, I'm actually getting further and further away from the original random weight setting, right? So if I were to do it that way, you can imagine that, then learning each of these patterns is not fair for each pattern, okay? So that's why we hold all these learning deviation patterns first. Then when we finish learning all 8 patterns, these are fairly all relative to the random, right? Then we add their composite contributions to the random at one shot. So we call this approach batch updating. You will hear this a lot in AI literature. We do batch updating. We don't do instantaneous updating. We do batch updating. Okay? And the reason is we want to learn always relative to a frozen original state. Then we learn this whole batch, then we update the original state. This way, each pattern gets a fair learning chance. Okay? Now, is this neurally correct? No, it's not. Our brain does not hold things before learning, at least not passively. Actively, you could. You could say, wait, hold this first in your thought, and then think about something else first, then learn something else. Yes, you do it consciously, yes, you can. In that sense, there is a psychological neural equivalent, but implicitly, I don't know if your brain is so smart to do that on its own like that, right? I mean, in terms of the brain's biology, low-level mechanisms, okay? So this is the question here. How exactly is this implemented? I'm not sure in psychological real life, right? Yeah. So this part is this inner loop and then going out to the outer loop after you finish for all patterns is jointly this batch updating mechanism. Okay? You get this part? Again, this part is not obvious in the reading, and it only comes out if you are actually implementing the code. All right, so if you're okay with this, then that's it. You have trained your neural, you have sort of gone through, because the rest are just qualifications, okay, like further calculating error and total error and all that, okay, to chart the performance. But essentially, you have done setting up your architecture, taking into account the bias weights, feeding forward, calculating the error, back propagating it back, and then holding things in, and then doing batch updating. So you have learned two things in this implementation that was not in the original theory today, is that in implementing the code, we realized that we have to do a normalization thing via the bias units, and we have to do batch updating, okay, because of the fair learning. As opposed to Bayesian learning at each instance. Bayesian meaning that whatever you learn now is constrained by what you learned previously, right? Batch updating is whatever you learn now is not constrained by what you learned previously, okay? So just these two additional mechanisms or concepts to add, to extend from previous theory that become more obvious here when we are running the coding translation of the theory, okay? That we have to take care of normalization and we have to take care of batch updating, fair learning, okay? Otherwise, the code as described, the algorithm as described doesn't behave very well. In fact, it wouldn't learn at all as far as I know, okay? Or at least the way it learns is not what we want. Okay, so this is the training, and the testing is by far easier, but so this is the training. Any questions first? Any immediate questions? Okay, I mean, there's a lot to absorb, okay? And obviously, you have the code, you can go back and digest it one step at a time from my explanation today and the video recording. And I will fix the errors. If I fix the errors, when I fix the errors, I will send an announcement to let you guys know, okay? All right, so the final part that I want to go through today would be the testing part, the testing code. And that by far is easier than the training code. Okay, because the testing code is just feed forward. Testnet. For testing, okay, here, all you need is the train weights So whatever was from the trained perceptron. The input pattern that you want to test, which would be like in the Hopfield network, you know, we had the original thing and we wanted to remember we distort it, right? Okay, or we don't distort it, you know, depending on how much distortion you put. Well, here the input is that the pattern that you distort or the original pattern you want to test, and the units layer thing, which is again to tell it that it's going to have how many architecture kind of thing. You do need that. I guess I could derive it from the input W, but again, I was lazy that way at that time. In any case, you just give it this information. The train weights, the testing input you want to test, the idea being that if the weights have been trained correctly, then when you have a test pattern, one test pattern you give in, it will give an output pattern that should be O. That should be the desired output, right? Okay, that's the idea here. And so this is similar. It's just been a bit modified because we don't now need the bias weights. W actually has bias weights being learned in there, remember? Okay, but now we don't need it, so we can remove that. And then other than that, we just implement the activation function here. This is the same thing as I did before, the logistic function that is more precise, okay? This is different is that if, this is because this takes into account the bias units again. There's bias weights in there. I just want to tell the network that because, you know, if you are an output layer, then you have no bias weights to worry about. But if you are not the output layer, then please do not use the bias weights in calculating the activation. That's all. All right? So if you are the output layer, don't use the bias weights. If you are the hidden layer, don't use the bias weights. If you are the output layer, you don't have to worry about it. Okay? So don't use the bias units. So that's all these qualifications only. So that's it. That's the testing. It's just basically the same feed forward, okay? Just with a bit qualification, that's all. All right, so then the rest of the code, so any questions about testing? Should be pretty straightforward. The rest of the code is just about the evaluation, the standard things we do. So if we create a distortion pattern function, so just like in the Hopfield, we have some original pattern and we want to distort it to, you know, kind of test the limits of the model. So we create some distortion challenges to the input and how much distortion we want, and it returns a distorted output, okay? And some plotting functions. So I guess I should run this. Okay, I should run this, and I can run this, but I'm not going to use it. Okay. All right, so some plotting, setting up and all that. Okay, so then just to test to see if my code works is that I have a sample input with a desired sample output. And my hyperparameters right now, I'm going to use 10,000, okay? Epochs. It will run the training 10,000 times. It takes a while. And my learning rate is 0.3. And my mu is 0.7, okay? So it's gonna not learn so fast. It's gonna have a bit more memory, and my error tolerance is 0.001, okay? This is what number range? This is sort of a recommendation. It's from the assignment. You'll see the assignment that it will recommend this to you, okay? And I'm gonna train it on a 10, 3, 4 network because, so obviously, this input units layer and the output units layer is fixed. Because if your input is 10, size of 10, and your desired output is size of 4, your network must be 10 something something 4, right? Can be something else, otherwise it will not be able to do it. Okay, so that's the only thing you need to worry about in terms of the architecture constraints. Okay, so I'm going to train it on a 10.3.4. I want this multi-layer perceptron 10.3.4 to learn this mapping between A and between O with the 10,000 epochs, error 0.001, eta is 0.3, and mu is 0.7. And I'm going to have initialize it with no pre-trained W. Okay. Now let's see what it does. Okay. Oh, yeah, I haven't implemented this. Okay. Now let's see what it does. Okay, it's going to run this 10,000 times. Takes 1 minute, 40 seconds, something like that. Okay. Or maybe 1 minute or so. So as I said, my code does not spit an error out now because algorithmically, loop-wise, it's fine. The numbers, the range, and it's to do with the empty arrays being initialized with some numbers, where I want actually it to be initialized as empty. And so I have to fix that. So past 1 minute, 53 seconds. I mean, I don't have to train it 10,000 times. I can train it like 3 times just now when I try it, right? Just to demo it. But I want to show you the extreme case, okay? All right, done. Okay, so at first, the error of the difference, the variance of the pattern of the network's output relative to the desired output, the variance, right, was around 12, whatever that number is, okay? Okay. Then, very quickly, I suppose, around trial 10 or 20, it quickly dropped to 8, and it didn't get better from there. Okay, so already I know that it's because of those whatever initializing, it didn't drop to 0. What I wanted, and then it hit 10,000 because I told it to learn for 10,000, right? And it didn't settle to the error 0.001 that I wanted. So I know that it didn't really learn, but there was no like operation error. Okay, it did it 乖乖的做，只是做得不好这样子。Okay, that's what it is. All right, so I have trained now. So now I have a WT. Okay, and my WT WT. Yeah, my WT has size 10,001 because the original WT, and then now I have 10,000 training instances. The WT is the output from the, see? Okay, the train net, it trains and it outputs WT. Okay, so the train network is in WT, and there are 10,000 iterations of this. Obviously, what I want is the last iteration. Okay, and the last iteration would be WT minus 1, the last one. Okay, the length of this is going to be 2. The length of this last of the 10,000 iterations itself is of size 2, length 2, because remember, I did it as a 10, 3, 4 network, which means I have 2 layers, 10 by 3 and 3 by 4. In fact, I have bias units, so it should be 11 by 4 and then 4 by 4, because the output does not have bias units. So to check that my code did it correctly, I will now show you that WT, the last one, the shape of the first layer is going to be 11. Well, these are the weights, okay, and it's going to be 11 by 4. There you go. Okay, 11 by 4. And the next one will be 4 by 4. Okay, does that make sense? Okay. Then I want to test this last weight set. I don't want all the 10,000 iterations. I only want the last one. So I'm going to test weight, train weight set last one. And I want to test it on the second input. Okay, so I want to test it on this one. 0, 0, 0, 0, 1, 0, 0, 0, 1. And it should have output 1, 0, 0, 0. Okay? This one, let's see, it's 10, 3, 4. Let me set it up so that's correct. There you go. Okay? And you see, if I test it, I tested it on 0, 0, 1, 0, 0, 1, right? And it should give me 1, 0, 0, 0. But instead, what it gave me was, so this is the input. Okay, this row here is the input. Okay, this is the hidden layer activity that it forward propagated. And this is the output layer activity, which is all 0.5. Okay, nonsense. Okay, all right. So this is where my code, I know that it didn't learn. Okay, there's some setting error there. But essentially, if it did learn, what should come out would be, it's not going to be exactly 1, 0, 0, 0. It will be something like 0.9999, 0.98 some, 0.9 is 1, 0, 0, 0. So it's supposed to be something like maybe e.g. 0.98, then 0.01, 0.05, and 0.0, maybe something like that. Okay? So in other words, it approaches, right? Okay? If the network is trained correctly, because we are using the sigmoid function, okay? Because of sigmoid giving float outputs, okay? Then AJ is not binary, but approaches. Okay? Because obviously, see? Yeah? It's asymptotically 0 and 1. So the output cannot be equal to 0 and 1 exactly, but it approaches 0 and 1 asymptotically. So the output you should expect is not going to be binary ones and zeros. It's going to be floats that have that number. And it has the capacity to range in any number in between 1 and 0. In this case here, it's all 0.5. This is all wrong. Okay, all right. Okay, so just barring the kind of like bug in the code for now, which I hope to solve by next week, any questions about the coding implementation, training, and testing? Oops. Yeah. Any questions at all? Okay? Not okay? Yeah. So like how to decide units layer architecture, right? Right? Yeah. Okay. So the input and output are fixed. That one you can't decide. This totally determined by your problem set, your data problem set, right? The data table. Okay? For hidden, this is the empirical experimental question. This is precisely the experimental question. So it's like, depending on my input-output size. So let's say I have input is 10, output is 4. And also, the nature of the mapping between my input and output. Let's say my input and my output mapping are all orthogonal. They're all independent, okay? Or they're not. Maybe they're not linearly independent, right? Okay, so these complexities in the mapping and the size will require you to experiment with the different hidden architectures. So how many units, how many hidden layers, and how many hidden units per hidden layer? Those are experimental questions. The principle is this. If you have, so that's why so if we go to the, should I? Yeah, I guess I can. Let me see. Let's go back to the blackboard. Okay, so I have this architecture, but maybe use a fresh one. So I'll categorically state here, okay? The rubric, the principle to think about when deciding how to set up your hidden layers is essentially all determined by the input-output mapping complexity and the size of those input-output, of course, but more really their complexity, okay? And your goal, which is a function of the complexity as well, in the sense that if the input-output mapping is very, very complex, then you might need deeper layers, right? Or similarly, if your goal is to capture something that you think is very complex in the input-output mapping, then you need deeper layers, all right? So goal and truth, the idea here is that this brings out the idea of goal versus truth. It may be that your input-output mapping actually is very simple. You are overthinking it. You think that there's something deeper in it. Your goal is that, no, there must be something deeper that explains or causes these two things. It can't be so simple, okay? So you are deluding yourself, all right? So therefore you design, because you believe that there should be something deeper, therefore, like H size should be like deep, like 10, 4, 4, 4, 4, and then 2, something like that. Okay, you are deluding yourself if your goal is that you think that the output between 10 and 2 is something very complicated. So you overkill. You give it like four hidden layers. It may be, but likely not, right? Because it's a 10 to a 2 thing. So in a way, how many ways? 10, yeah? No, sorry. It's 2 to the power of 10, right? Or 10 by 2 to the power of 10. Yeah, right? Some permutation of the possible combinations that you can get from a 10-2 pattern. How many possible weightings can there be? Permutation. You can think about it, the complexity of it. So this is all about complexity. Okay. My argument for people, and complexity is notoriously hard to define. My definition of complexity in bits per volume or area is complexity. Okay. How many bits you can squeeze into this one small area? That's how complex that thing is. Right? Okay. Or conversely, per time. How many bits are being computed in this small amount of time, in this small amount of space? That's how complex this operation is. Okay? And in some ways, it is capacity, right? Bits per time, bits per second, something like that. In any case, what determines how many layers is about the complexity of your inference about the function of the networks, your goal, or the truth of it, that it really is that complex. And therefore, in order to effectively map it, you do need that number of layers or the number of units. Okay? Right. That being said, there are certain, so this is the overarching principle. That being said, you think about it, this shape means your input to output is the same size, or roughly the same, but you have some sort of a bottleneck in between. What are you doing? You are squishing the bit space of the input to a smaller basis bit space, okay? Then expanding it to another arbitrary bit space. Think about that. Essentially, this is itself a W of another network. You can cut it. Such that, sort of, right? And this part, except that this thing can backprop to further on. But essentially, there are two separate, you can dissect it and think about it that way. So you are squashing things, then you are expanding things. You are taking the expanded squashed error and then putting back into the squashed expanded change in weights. That's what you are doing when you do it this way. So that is another way of thinking about how to decide, well, about my hidden units, how many should I have? Because how much do I want to compress? And how much do I want to allow for the expansion? So that because the more I expand, the more I'm projecting few information to more information. The more I compress, the more I'm projecting a lot of information into a reduced dimension. Okay? This is how to think. That's one way to think about it. Okay? The other simpler way that implies that this is the same as this, and implies that this is the same as this. Right? A hidden layer that compresses information, a neural network backpropagation multi-layer perceptron that compresses dimension, and this one is expand dimensions. Okay? So then opposite, if you do it this way, compress and expand, you can obviously also expand and then contract. You can do that too. Okay? And all other instances are just, nothing. It's just carrying through. Okay, no compression, not just exactly flat. Anything else? That's pretty much it, I think. It's either expansion, contraction, or relatively speaking, no expansion or contraction. That's all. Right? Yeah. Well, that's recurrence. So we'll come back to it at the end. Okay? But let's assume first no recurrence. Assuming no recurrence. No recurrence means that this is just forward, backward pass. There is no kind of, whatever you take, you carry it on to the next iteration and all that. Sort of a Bayesian thing now coming in, but yeah. But at this point, let's say assume that we are using whatever algorithm we've been talking about before. If we do it this way, then there's only compression or expansion like this, relatively speaking. So in terms of how many hidden layers, how many units per hidden layer, well, the way to think about it is that what's the complexity that you are testing, what's the complexity that's in the data, and the fact that when you use different numbers and sizes of hidden units, essentially what you are doing is compressing or expanding dimensions, right, for the mapping. And therefore, you are giving your output you are constraining the degrees of freedom that your output can vary relative to the input, right? Yeah. And so to the extent that those degrees of freedom work to achieve the mapping efficiently, then that's the answer. That's the answer. Yeah. Going back to statistics, it's the same, because in statistics, having too many degrees of freedom is inefficient, right? You want to have a penalty. I mean, I can have a perfect model that will account for everything, and then I can explain the data perfectly. But then I have to hold those number of parameters. Same thing. Maybe I don't need so many. I only need this flat one. That's enough, right? Oh yeah. Well, I forgot to mention. Yeah. So it can be like you can have long, or you can have, very short, right? Or like, okay, as in the length of the model, to how deep it is and whether it's compressing or something, or you can even do, right? Right. So you can. It's all compression, expansion, and how long it is. So the more parameters, the more degrees of freedom you have, the more you have to hold. The model might perform well, or it might be overfitting. We will deal with all of this at the end of the class. Yeah, it's the same in statistics, right? It's the same. So in statistics, we don't really want a model that has many terms. We just want one that really works very well with very minimal error. In neural networks, that's not really like, we don't care that the model has to be conceptually interpretable. But in that sense, it's okay for us to have quite a few number of parameters, yeah? Many parameters. But the concern is still the same, that in a sense that if you have too many parameters, then maybe the model is not really learning anything, it's just trying to fit to the data, it's overfitting. And in that case, it's like the same issue that the statistical model meets. My argument, however, is that, well, but maybe through the model, it does want to overfit. To a biological system, you do want to overfit, and you are always overfitting. That's all, until you are wrong, and then you overfit again. You keep overfitting. Yeah. Okay? And the only thing that prevents you from overfitting is how much food you eat. Because if you overfit, it takes energy, right? And if you have energy to overfit, you will keep overfitting. But if one day you run out of food, you can no longer overfit. That's it. You've reached your limit. You cannot overfit anymore. You die. That's it. Okay? Yeah. So in that sense, what I'm saying is that the purpose and logic, 精神, the spirit of what statistics is trying to do, what machine learning is trying to do, and what biological systems are trying to do, they are trying to be efficient in their own ways, but their metric for what is efficient is different. Statistics is what is explainable by some base core factors. Machine learning is how can I best minimize the error with the least, whether it's explainable or not, that's not the final goal, right? The final goal is to suck up all the error, to minimize it. Biological system is, no, cannot die. I cannot die. Right? It's not about understanding anything or minimizing any error. I mean, those come into it, but its final goal is really to survive. So they have different purposes, and in biological systems, machine systems, statistical systems. So this goes on to that. How does it solve that problem by creating the appropriate number of hidden layers and all that? Yeah, depends on those concerns. Okay, any other questions? Does this help you make sense about LLMs? Do you not think LLMs are very magical? I mean, yeah, it's more complicated than this, obviously. There's a lot of other contingencies, but the core is sort of like this. It will become more obvious later on. At the end, we do talk about recurrent neural networks and the principles of how language prediction works, symbol prediction works, okay? Okay, so if there are no other further questions about this coding, today we have basically dived into the code part and additional issues that arise because of that, right? Beyond just the theoretical last week, okay? Sorry about the bug and all that. I hope get it sorted out by next week. Next week we will come, hopefully the code is in good shape, and as with the hot field, we will use it to evaluate certain things so that the usage of it, the application of it, and how to modify it, or even how to create it yourself becomes even more concrete, hopefully. And as usual, the goal is to help you to do that so that you can address the assignment, all right? And the assignment for the backprop, just to preempt, will be the same kind of concept as the assignment for the hot field. The first few questions help you set up, okay? Tell you to implement this basically, and then test this, some simple things, and then ask you some simple interpretations, help you set it up. Then the last few will be like, okay, now that you set it up, let's break it, let's try push it, kind of thing. Okay, so it'll be the same for backprop. All right, okay, so if not, then that's it for today, and I will see you next week. Any questions? How about the assignments? Any issues about the hot field assignment so far? People are okay? That will be due next week. Yeah, all okay? I emphasize again, the first few questions you all should be okay. The last few questions might be challenging, and in no way do I expect you to be able to answer everything and answer everything in a very beautiful way or whatever it is. The point here is to give you this, they're more like tutorials, to get you to get your hands dirty and do it. And in general, I don't penalize you even if you don't complete everything, but it's more like, did you get past this and demonstrate that you are working through the solving a neural network kind of simulation problem. That's it, okay? So that would be it. And so I think if you have no questions about the assignments, then hopefully everything is okay. And so I think next week will be okay. And next week I will release the backprop assignment then, so that you can work through it from then onwards. Maybe it's open already, you can take a look if it is, but the due date is not set yet, okay? All right, thank you, and we'll see you next week.